For arithmetic, the processor provides the set of operations you would expect. There's an add, subtract, multiply. There are bitwise operations like shifting left and shifting right. These are the signed versions. The A stands for arithmetic, so signed versions. And then there's shift left and shift right. Those are the unsigned versions. For shift left, SAL and SHL are actually the exact same operation. So which one you write in assembly code doesn't matter. Which one the disassembler picks when it's going for machine code, it just has to guess one of them, or maybe it always picks one of them. And then there are bitwise operations like XOR and OR. Each of these operations takes just two arguments. So normally for add, at this machine level, you might think there's three arguments, two things to add, and then where to put the result. But one of the arguments and the place to put it are sort of the same in all of these operations. So add takes a source and a destination. Those are just two numbers to add, but it also uses destination as the place to store that. So that might be a register or a memory address. It's going to put the sum of the two numbers there, replacing one of the arguments to add. Sub is subtract. The order here is unfortunate in a way, right? It's source and destination, and the destination is always second, but sub means subtract the destination minus the source, right? So if you tried to put a minus sign in between here, it would be backwards. You have to imagine moving dest before source and putting a minus sign. For most things, the order doesn't matter, like multiplication or XOR and AND. For shift, it does matter. Again, it's dest shifted by source. And because destination is at most 64 bits wide, the source here is always going to be just a byte. You can never shift by more than 63. There's a few shorthands. There's an increment, decrement, negate, and not operation that take just one argument, and that's because the other argument is implicit, either +1, -1, or 0 minus destination if you wish to think of it that way, or not is just flipping all of the bits of a destination. Finally, there's an operation that's like arithmetic, but it's sort of more like a move in the way that it's written. So LEA stands for load effective address, and it's just like a move in that it takes a source and a destination register, but it doesn't look into the place that the source is pointing to. So the source argument is always one of these addresses that you would normally interpret as looking into memory, and it doesn't actually look into memory, it just moves the address over into the destination register. So for example, if I say load effective address for RBX RSP, this means add RBX RSP and then add 4 to that, and then put that address that you compute by adding those three numbers into RAX. Don't go look in memory like a move queue was. In other words, the processor has all of this machinery to do these kinds of simple and useful arithmetic for addresses and moves, and so it just lets you use that directly to do common sorts of arithmetic. So this is going to, again, add RBX plus RSP plus 4 into RAX instead of using two adds, instead of using two separate add instructions. Here's another example. This says compute the address that you would look up at RSP, right, and just put that in RAX. Don't actually look on the stack, just compute the address where you would look with a move and put that address into RAX. So this one is less useful because it's just the same as moving RSP to RAX, but it's what falls out of the grammar of source descriptions.